So the next speaker is Sergei Gukov, and the title of his talk, A Polynomial B-Model and Test Duality. Please.
Thank you very much. Well, we're all enjoying this network of knots and tangles. I want to thank the organizers for their hard work and for putting this wonderful meeting together in such a lovely location. Also, as by now is standard in this conference, my title is not, or the title I originally gave does not fully reflect the content of my talk, but it's kind of nice, and as one of my collaborators suggested, it would be good to have a word and starting with C. So unfortunately, I have only A, B, and S, and some of this we'll see in the talk. So, conclusions, and this is a good strategy for gong show talks. In this talk, I'll describe some recent developments which can be formulated as conclusions for good old Chern-Simons theory. So here I try to summarize it in this particular way. We'll look at some hidden symmetries in Chern-Simons theory, and the symmetry here is very suggestive of electric-magnetic duality, where electric group is replaced by magnetic group, and coupling constant is inverted, so we'll talk about this. Then there are some other conclusions which I summarize here, and most of the conclusions on this list can be formulated just within good old Chern-Simons theory, even though it would be very hard to guess or predict any of them or understand properly without knowledge of string theory. That's why it's actually a string theory talk, and as you'll see in most of our discussion today, we'll be talking about strings rather than Chern-Simons theory, but that will be my starting point here. Chern-Simons theory is defined by cubic action, as everybody knows, and it's a wonderful physical system. It's an interesting quantum field theory. It's a gauge theory. It's interacting. It's non-Abelian. It has very long history associated with exact solution of the theory, which was already mentioned in a number of previous talks, and has lots of applications ranging from quantum computation to condensed matter systems, in particular quantum Hall effect, to topological strings, and many other wonderful applications. So the setup will be the following. We'll look at Chern-Simons theory on a three-dimensional manifold M, and depending on the context, M may or may not have a boundary. And we'll try to compute partition function, so it will be a path integral with the Chern-Simons action and the exponent as usual. There is a constant here, which is the coupling constant. I'll denote it by h bar. And the whole object obtained in this way is something that's associated to a three-manifold choice of the gauge group and the coupling constant. Because the action does not involve metric, although this requires some subtle discussion, the whole partition function is a quantum invariant of a three-manifold M, and that's why mathematicians love this theory as well for many applications. It will be interesting to compute this partition function, see if it characterizes manifolds, knots, or other toys in three-dimensional topology. For us, it will be important that this invariant depends on choice of the gauge group, G, which was obviously assumed when we took the trace. And it also depends on the coupling constant h bar, or equivalently on the exponential of the coupling constant, which is denoted by Q. As a result, the partition function, the main object here, the topological invariant that we'll be studying, is a power series in Q. So when you try to solve the theory, produce such a topological invariant, what you're expecting is some kind of power series in Q. And to a mathematician, when you see a power series, natural question to ask, does this power series have any nice modular properties? If you write something as a power series, it's natural to say that Q is exponential of 2 pi I times a tau, and try to make a modular transformation on tau. See if series remains the same, transforms in any nice way, or something like that. Well, here there is not much chance of nice modular behavior, because in real Chern-Simons theory, as studied by Edward more than 20 years ago, the topological invariant that comes out depends on Q, which has to be a root of unity for theory to be nice and good and physical. In particular, h bar here is 2 pi I over integer, and therefore, if you try to apply modular transformation to this particular tau, here you'll find that it's modular transform is 2 pi I times the integer. So q, which is exponential of that, will be equal to identity. So there is not much chance to expect anything modular or anything nice in that respect. And if you try to evaluate, for example, this partition function on a complement of a figure-8 knot, which mathematicians love, that's why they made a sculpture of it, and it appears as a logo of Clay Mathematics Institute, you actually find that the power series in Q that we were discussing is not much of a power series. It's actually a polynomial. And this, of course, is the fame of Edwards' work on John's polynomial and Chern-Simons theory. So the power series stops after a few powers. You have several terms. And for this particular knot, which will be one of the examples in my talk, it has 5 terms. And of course, there is no way this could be a modular function or modular form. However, you can try to do various experiments, and to me personally, first hints of this hidden symmetry that I'll try to explain come from experiments that we did with Don Zagier a couple of years ago. At that time, we were trying to study analytic continuation of Chern-Simons theory to complex value of the coupling constant. And it was already clear at that time that if you try to analytically continue in variable q, which starts its life as a root of unity, but then you try to push it away from a root of unity, you simply have to analytically continue the gauge group also to complex group, which I'll denote GC in this talk. This particular aspect was explained in a wonderful paper of Edward. Even though he was giving us very good review of recent work yesterday, this paper, I think, was not mentioned, and it sheds a new light on analytic continuation in Chern-Simons theory. In particular, it makes it absolutely clear that this has to be the case. So the experiments that we did at the time were the following. Indeed, if you try to analytically continue partition function of SU2 Chern-Simons theory, this was answer for G equals SU2, then its complexification would be SL to C, you indeed find much wilder life out there. In particular, you find that this simple polynomial now has analytic continuation, which looks like this. It can be written as sum, and here you have nice product formula for each term, and now it's a real power series in Q. So this is now at least more meaningful for the purposes of asking questions about modularity and behavior like this. And surprisingly, this result does have nice modular feature, but it's very delicate, very subtle. So if you took a course on modular forms, you know that there are roughly different hierarchies of modular behavior that you can encounter. If you try to start with a function, z, for instance, z of q, and apply modular transformation, one possibility is that the result after modular transform is the same function. That would be called modular function. Then it may happen that the result differs from the original function. And mathematicians introduce what they call automorphy factors, and so on and so forth. So this leads to a hierarchy of modular forms, almost modular forms, mock modular forms, and so on in increasing degree of complexity. This beast, this simple expression here, is none of those. It has much more delicate modular behavior, which is very wild, but if you notice, you love it. And that was experience of this work, these observations with Don Zagier. So this was so wild and interesting that Don said, let's call this quantum. And this basically opened the door to a completely new subject in mathematics. Now, there is a whole class of functions characterized as usual modular forms by a set of properties and their behavior, which is called quantum modular forms. To me, however, this was always strange. And to be honest, I was ashamed for all these years to publish this because it was a good set of observations, beautiful mathematical formulas, but I couldn't see nice physics home for this behavior, in particular for quantum modular forms. Of course, this didn't stop my mathematics colleagues, and they completely ran away with it and developed a whole new area of mathematics. Now, luckily, there is a nice home for this behavior, and of course, once you see a group replaced by magnetic dual, and you see coupling constant inverted as it happens in n equals 4 super-Young Mills, you think that there should be a realization of this setup in string theory and hopefully in n equals 4 super-Young Mills or connection with one of these 5 brane theories that was discussed earlier and that we'll consider later today. So in this talk, we'll start with 6-dimensional 5-brane theory, 2,0 theory, which was reviewed already in Greg's talk in great detail. And actually, it's nice to talk after this wonderful review because it sets a good stage. And many of the ingredients that we'll be doing now are highly motivated by what Greg described to us. And we'll take the space-time in 6 dimensions to be a 3-manifold M, same manifold on which we just discussed Chern-Simons theory, and a 3-sphere. Actually, we'll also consider various degenerations of 3-sphere when we'll do various morphisms to it. So such theory of such 5 branes on this particular product of 3-dimensional space-time was looked at in the supergravity context and work of Jerome Gauntlet, Kim, Dan Waldron, and various other collaborators. And this work was very nice, very beautiful, but then it sat for years without any good applications. In particular, there was no microscopic approach or no computational tools which allowed to study, say, partition functions or draw connections between different ingredients in this story. And resurgence of the interest in this field was last year, and we had lots of beautiful papers written on the subject, which describe various aspects of the system, and this is what I'll try to summarize for you in this talk. As Greg explained to us, the motto or slogan in this game is compactify and compare. So we'll try to compare 2 different compactifications of 2,0 theory, first on a 3-sphere, when we obtain something on a 3-manifold M, and in this talk I'll try to convince you that this something is exactly the analytically continued SL2 Chern-Simons theory, or we can compactify on 3-manifold M and obtain some effective, I'll put it in quotes, 3-dimensional supersymmetric gauge theory, which should know whose spectrum should depend on choice of the 3-manifold M. In this way, it's very reminiscent of geometric engineering, when we start with a bigger theory and compactify on some curved space and look at the effective theory whose spectrum and interactions depend on the geometry of the space M. So this is, if you wish, a baby version of geometric engineering. Now, as Nati stressed yesterday in his talk, we have to be very careful to preserve supersymmetry. And the way we are going to do this is via some sort of partial topological twist along 3-manifold M, and what this means is a combination of, we'll try to form a combination of R symmetry of the 2,0 theory with rotational symmetry. That was more or less the standard way until a few years ago. And along 3-sphere, we'll put the theory in omega deformation, and this connects with many recent developments, essentially a new line of developments that, again, was beautifully summarized in Nati Seiberg's talk yesterday. And then we'll try to follow these 2 reductions, and our slogan in this game will be to compactify and compare. On one hand, we'll get something, some universal theory. If we take 2 5-branes or 2,0 theory of type A1, we'll be talking about SL2 theory on 3-manifold M, and theory is the same because we always gonna take 3-sphere as this part of the geometry. On the other hand, in another line of compactification, we can compactify on different 3-manifolds, and here we'll obtain many different n equals 2 3-dimensional theories which do depend on the choice of the 3-manifold M. And on this part of the space-time, we'll put this theory in omega background, which on one hand will take care of the supersymmetry, and on the other hand, will allow us to compute partition functions via localization, as was reviewed in previous talks. But first, even though this comes motivated by compactification of the 5-brane theory, you can actually forget about 5-brane as in the IJT relation and simply take these 2 corners and say that there should be some kind of duality which relates 3 manifolds and 3-dimensional effective gauge theories on a 3-sphere very much a la AGT, where the spectrum of the theory is determined by the geometry of the three-manifold M, and by following supersymmetries, it's very easy to see that this effective geometrically engineered theory has to have n equals 2 supersymmetry in 3 dimensions, and therefore one of the goals of this program could be just to identify the dictionary between 3 manifolds and 3-dimensional n equals 2 gauge theories. In particular, build a dictionary which contains translation between many properties of 3 manifolds to corresponding properties of n equals 2 3-dimensional gauge theories and vice versa. So as you'll see, this dictionary is surprisingly complete and is very, very rich, just like 3-dimensional manifolds have very rich geometry and very rich topology. This, again, has to be compared with AGT correspondence, where there is analogous split, as Greg calls it 2+4, where 2-dimensional theory is being compared to 4-dimensional theory. Here, 2-dimensional theory is not supersymmetric. It's a conformal Liouville theory or Toda theory, and here we have relation with supersymmetric 4-dimensional gauge theory. Same thing here. In this corner, it will be non-supersymmetric SL2 Chern-Simons theory, and here we'll have supersymmetric quantum field theory. Now, one of the objects that's being compared in the previous correspondence is the Hilbert space of n equals 2 4-dimensional theory on, if you wish, time direction across a 3-sphere, and this gives you a certain Hilbert space which depends on parameters epsilon 1, epsilon 2 of the omega deformation, and this has to be compared with the Hilbert space or space of conformal blocks on the Liouville side. Here, one of the comparisons, there could be many, but one of the comparisons can be made at the level of partition functions. So what one can compare is a 3-dimensional partition function of this effective, geometrically engineered, if you wish, n equals 2 gauge theory on a 3-sphere, which depends on ratio of equivariant parameters epsilon 1, epsilon 2, to partition function of Chern-Simons theory. For instance, I showed you the formula for complement of the figure 8 knot, which was written in terms of h bar or q, and we'll be trying to compare these two objects, among other things. In fact, the connection with 2D, 4D correspondence or AGT correspondence is not just an analogy, it is fully consistent with it, because this relation, which is one of the essential points of AGT correspondence, the relation between space of conformal blocks and Hilbert space of the 4-dimensional gauge theory on the 3-sphere, can be nicely embedded in this formalism if you try to pick M, 3-manifold that we were working on, to be time cross Riemann surface C, as in the previous picture. In this case, SL2 Chern-Simons theory on a 3-manifold M, when it has the form time cross a Riemann surface, Chern-Simons theory associates to this 3-manifold a Hilbert space, namely Hilbert space of states in Chern-Simons theory with a spatial slice C. And this happens to be exactly the same as the space of conformal blocks in Liouville theory. So you can think of this relation first. It doesn't have anything to do with 5 branes or 2,0 theory or supersymmetric gauge theory. And it is simply a relation between Chern-Simons theory, Hilbert space on a Riemann surface C. Here there is our good old friend h bar, the coupling constant. It's related to the space of conformal blocks in Liouville theory, usually parametrized with the parameter B, associated also to Riemann surface C, and relation is as such. And then can be compared to the Hilbert space of 4-dimensional supersymmetric gauge theory on a 3-sphere, as was beautifully explained in a work of Nekrasov and Witten, amplifying the claim of Alde, Gayotto, and Tachikawa. So first of all, you learn that this proposed correspondence between Chern-Simons, SL2 Chern-Simons on a 3-manifold M and 3-dimensional supersymmetric gauge theories is, if you wish, an extension of AGT correspondence, and it's also fully consistent with it. One thing that you learn in the process is relation between the parameters, that coupling constant in Chern-Simons theory that I called h bar has to be equal to 2 pi I times b squared, where b is the parameter often used in Liouville theory, and epsilon 1 and epsilon 2 are again parameters of the omega deformation in supersymmetric side. OK, so let's return to the most general case for now, where M is any three-manifold, and try to extract some lessons when h bar, which now we know is proportional to b squared, goes to 0. This limit, which is described by b squared going to 0, or h bar is small, is semi-classical limit from the viewpoint of Chern-Simons theory, according to the dictionary that I started painting for you in the previous slide. So this limit should be fairly easy to understand, and hopefully we can reproduce something simple. And it also has a very nice geometric meaning in the framework that appears here. The reason is that, as we just identified, h bar is related to b and is also a ratio of epsilon 1 and epsilon 2. And epsilon 1, epsilon 2 parameterize aspect ratio of the three-sphere in 3 dimensions. So one way to think about supersymmetric compactification on a three-sphere, as Nati Seiberg explained to us yesterday, is to think of compactification, in this particular case, on squashed sphere, or ellipsoid, as it's sometimes called, whose aspect ratio is exactly epsilon 1 over epsilon 2. So in particular, what happens in this limit when h bar goes to 0, or epsilon 1 over epsilon 2 goes to 0, the three-sphere degenerates in a product of R2 cross a circle. So the aspect ratio of the sphere is sent to 0 or infinity, depending on how you're going to look at it. And now we have a nice circle in the picture, which is very nice and useful because, as was explained in Greg's talk, six-dimensional theory is mysterious, but at the moment we have a circle in the geometry, we can immediately compactify on the circle and produce something that we can study. We have gauge fields, we have Higgs fields, and we can understand the system in the limit where, for us, the three-sphere degenerates into R2 cross S1. So here we can replace 2, 0 theory by n equals 2 5-dimensional superrank mills by compactifying on a circle. And here we have same old corners, good old corners, except that three-sphere is replaced by R2 cross a circle. Now, what we call partial topological twist along M is very easy to understand in this semi-classical limit, because now it's very easy to perform topological reduction of 5-dimensional superrank mills and try to see what it could potentially give us. And performing this twist is very easy. 5-dimensional superrank mills has rotation symmetry, which is SO5 in Euclidean space, and also has SO5 R symmetry. So if you try to compactify this 5-dimensional theory on generic three-manifold M, one obvious thing you can do, you can try to combine SO3 subgroups from here and here into new rotation symmetry SO3 prime. And this will give you a topological field theory whose spectrum is written here, in particular 5 components of the gauge field and 5 Higgs fields in 5-dimensional superrank mills produce this spectrum of fields here. In fact, this is topological twist studied many years ago by Blau and Thompson. And one interesting feature of this topological twist is that as a result of compactification, it has 2 gauge fields, 2 one-forms in 3 dimensions, which nicely combine in a complexified connection. And if you go a little bit further and ask what are the fixed points of supersymmetry charge in this topological theory, you notice that it localizes on solutions to the flatness equations for the complexified gauge connection. So by looking at the h bar goes to limit, we already know that along this direction, classical solutions or vacua of this 5-brane system are exactly complexified flat SL2 connections. And therefore, you expect that whatever this n equals 2 effective 3-dimensional theory is, from now on I'm going to call it T of M, theory that depends on the choice of 3-manifold M, geometrically engineered from M, if you wish. So one property of this theory should be that when viewed on R2 cross a circle, its supersymmetric vacua have to be in one-to-one correspondence with flat connections on a 3-manifold M. So this is our first evidence for the relation between space of supersymmetric moduli here in this theory T of M and flat connections on SL2 flat connections on a 3-manifold M. We'll talk about it a little later, but now is the time when I give you a couple of examples, and then you'll see where this dictionary comes from. I'll use in this talk 3 examples of 3-manifold M, and corresponding theories T of M will be summarized here. For example, the simplest and in many ways the strangest 3-manifold, which has lots of boundaries and corners, is tetrahedron. But it's nice because you can build many other 3-manifolds by putting the simplices together in a nice shape. And it's associated with a very simple theory of a single charged chiral multiplet, which is charged under a single U1 factor. And actually, it's important to introduce Chern-Simons level -1/2 to this theory, which we are going to call T1. Now, we'll also consider 3 manifolds obtained from Riemann surfaces by evolution and time with potential twists. And this is an example of such twist by an element, S element of SL2Z. It's associated to a theory which is usually called T of G, and in this case, G is SU2. It has a quiver representation like this, where there is a single U1, and it's coupled to 2 chirals of charge +1 and 2 chirals of charge -1. And example that I mentioned in the very beginning of a figure-8 knot sitting in a 3-dimensional sphere will be associated in this language, effective theory T of M that you obtain by compactifying fibrane theory on this geometry will be U1 cross U1 quiver gauge theory with levels -1 and +1 and bifundamental chiral multiplets as shown here. One feature of all of these theories that you may notice is that there are Abelian quiver gauge theories. So that's already something easy to see from examples I showed to you. Moreover, if we are interested in supersymmetric vacuum moduli of these theories on R2 cross S1, which hopefully should reproduce the space of flat connections on a 3-manifold M, it's useful to look at twisted superpotential of these theories. And we're interested in twisted superpotential of these theories on R2 cross S1. And it could be understood in 2 steps. First, let's compactify on S1 all the way down to 2 dimensions. Then you get a close cousin of our 3-dimensional theory, which is a 2-dimensional theory. And typically, it's some kind of n equals 2 super QED, because all of these theories are abelian, as you notice. And superpotential, twisted superpotential in such theories comes from one-loop diagrams where you have gauge field and chiral multiplets running in loops and leads to twisted superpotential of the familiar form x log x. Okay. Then we can actually turn on the radius of the circle, since we're interested in vacuum of the theory on R2 cross S1, as was predicted by the previous picture. And in this way, we get lots of colored Klein modes, which give rise and promote the x log x dependence to dialog dependence. So twisted superpotential in a theory on R2 cross S1 is combination of transcendental functions, dialogues, and looks a little bit complicated, not so much algebraic, but something nice happens if you try to follow this procedure. The superpotential depends on dynamical fields, which I'll collectively denote by sigmas, and also depends on various parameters, such as mass parameters, namely twisted masses, or Fayet-Leopolez terms. And one thing you can do, you can try to, first of all, minimize potential with respect to all dynamical fields. Since they're fields and fluctuating, they're allowed to go to minimizing value of the potential. And therefore, we should extremize potential with respect to them. But then we, of course, have to keep parameters fixed. However, let's introduce the dual or conjugate variables to the parameters, twisted masses, Fayet-Leopolez terms. And since I call all the parameters V, I'll denote the conjugate variables by U. So for each parameter Vk, there is a corresponding conjugate parameter Uk. I claim if you do this, something nice will happen. And transcendental superpotential, twisted superpotential, which contain dialogarithms, will produce for you a beautiful algebraic curve. So let me illustrate how this happens in a case, say, of a punctured torus, which via GT correspondence is known to be related to n equals 2 star 4-dimensional theory. This 4-dimensional theory has duality group PSL2Z. Well, naively, you could think the duality group is SL2Z, group of electric magnetic dualities with the T transformation. But -1 in SL2Z acts as a charge conjugation, and as I think was first properly explained in the nice paper of Danagi and Witten, the actual group, duality group, is PSL2Z, and this is nothing but the mapping class group of a punctured torus. Here, in this problem, we have only one parameter, according to the terminology I had earlier, namely the eigenvalue of SL2 holonomy here, which is identified with adjoint, mass of the adjoint multiplet in n equals 2 star theory. So there will be only one parameter v, and eventually only one conjugate parameter u, according to the slide we had before. To build a three-manifold out of punctured torus, we can try to evolve it in time, if you wish, at the third direction. And what this corresponds to is a duality wall in n equals 2 star gauge theory. And as a duality wall, it could interpolate between two vacua of the theory, which are related by an element of the duality group. Here, mathematician would call this transformation a mapping cylinder, because what it is, it's essentially a cylinder built out of punctured torus, where top and bottom differ by a monodromy, which is exactly this SL2 Z transformation of the mapping class group or duality group, depending how you look at it. It doesn't change the fact that there is single parameter in the theory, namely one parameter associated with the mass of the adjoint multiplet in n equals 2 star. So as a last step, we can take such a mapping cylinder and glue top and bottom together. What we obtain now is a closed three-manifold, and this is one of our examples, three-manifold M. And now we can follow this program. We obtain some theory T of M, which ought to have the following property. The effective superpotential in this theory, as a function of mass parameter for n equals 2 star theory, which I call V here, differentiated with respect to V, gives you a conjugate variable. And claim is, if you exponentiate U and V, what you find is that the space of vacua, or space of supersymmetric vacua here parameterized by twisted mass, forms an algebraic curve in terms of variables x and y. Sorry. It's quite a nice fact. It's actually easy to understand a posteriori, but it's rather nice because superpotential started its life as a transcendental function, namely sum of dilogues. Minimizing that potential gives you logs, still nothing algebraic. So appearance of algebraic curves is a little bit of a surprise, but written in terms of these variables, claim is that it is always going to be an algebraic curve. And in fact, it's not a random algebraic curve. It's a curve which has simple meaning in the geometry of the three-manifold M that we started with. So in particular, it's Chern not invariant in the case where M is a knot complement, called a polynomial of a knot, and it has many beautiful connections with the volume conjecture, generalizations of it, and has lots of applications in the three-manifold geometry. Plus, this curve, algebraic curve, which I described in my strings of three talk, has many similarities with spectral curves and Seiberg-Witten curves. Namely, it comes with a meromorphic differential. It plays essentially the same role as a spectral curve, and again, I tried to emphasize this many years ago, and at that time it definitely looked at that it has to have interpretation in supersymmetric gauge theory, because it looks like a duck, it walks like a duck, it quacks like a duck, so it has to be moduli space of something. So now claim is that it's nothing but the moduli space of 3D n equals 2 theory on R2 cross S1. And it is not surprising that moduli spaces in three-dimensional n equals 2 theories are complex manifolds. After all, supersymmetry constraints tell us that parameters in those theories have to be complex valued, and it's a little nice that moduli space turn out to be nice algebraic curves, but what is actually nicer is that these moduli spaces for very simple three-dimensional theories happen to be nice topological invariants, namely a polynomials of three manifolds associated with it. So here is an example. If you take this twist in building the mapping torus to be T times S transformation of SL2 times T inverse times S inverse, what you actually build is an example of the figure 8 knot that we discussed throughout this talk. In this case, as I told you earlier, the corresponding three-dimensional theory is a quiver theory with U1 times U1 gauge group and Chern-Simons levels +1, -1, and 4 matter multiplets. You go ahead, compute superpotential as a function of this parameter V, And what you find is indeed a nice algebraic curve, which in this case happens to be of genus 3. So the zero locus of this curve, a of xy equals 0, is of genus 3 and is given by this interesting equation here, which is, as you see, rather non-trivial. And it's actually a lot of fun to see how this curve emerges from the minima or vacua of the three-dimensional n equals 2 theory. In this example, it happens that the quiver description of the theory and Riemann surface have a nice relation, namely both are of genus 3. Honestly, at this stage, I don't know if this is an accident, that the Riemann surface can be visualized by thickening lines in the quiver, or this is a general property. That's an interesting question, and we are trying to understand whether it holds in more general theories. But this is some good observation to keep in mind. So before I conclude, I'll do only one more example, because this example is actually more fundamental and more central to what we're trying to do. Tetrahedron, which, as I say, is a rather strange three-manifold because it has boundaries and corners, corresponds to a very simple three-dimensional n equals 2 theory, which has single-charged chiral multiplet coupled to background field U1 with the Chern-Simons level minus a half. We call this theory T1, and if you want to look at supersymmetric vacua of this theory on R2 crosses 1 in order to find the corresponding A polynomial or the corresponding algebraic curve, it's convenient to use string realization of this two-dimensional, effective two-dimensional theory as a theory on a D2 brane in the NS5 D4 system, or the corresponding picture in the geometric engineering, where this is C3 and this is a single D brane. Both of these pictures give rise to a very well-known curve corresponding to CP1 minus 3 points. So the algebraic curve that I was describing, or the space of moduli in this baby example, is simply a three-sphere minus 3 points and can be visualized like this. But what's important is that three-dimensional partition function of this theory on a three-sphere that we talked about at the earlier stage is the same as special function called SB in Liouville theory, and is what's usually called quantum dilogarithm in three-manifold topology and construction of three-manifold invariants. Indeed, you can build any three-manifold M out of such tetrahedra by gluing them together in a suitable way, and therefore the partition function of SL2 Chern-Simons is obtained as a finite dimensional. This is not a path integral. It's a finite dimensional integral whose integrand is a rather complicated product of quantum dialogues. So these are special functions which, as h bar goes to 0, behave as dilogarithms, and therefore in the semi-classical limit when h bar goes to 0, you can actually see the effective twisted potential, superpotential that we were discussing before. But for generic value of h bar, this is a product of quantum dilogarithms, and the resulting three-manifold partition function for SL2 Chern-Simons is obtained as a certain contour integral in over products of such quantum dialogues. Therefore, taking the basic theory, three-dimensional theory associated to a single tetrahedron, and gluing it together to several copies of it with suitable gauging and applying the rules that Greg Moore described in the previous talk, we can hope to construct three-dimensional effective theory associated with a general three-manifold. And for a particular example of the figure-8 knot, which followed me throughout this talk, the partition function is actually not that bad. It contains only single integral and only two quantum dilogarithms in the integrand. So this is a very explicit, nice, concrete expression. And if you asked me where the formula on one of the first slides that I showed you related to experiments with Donza-Gear come from, it comes from this integral. You simply define partition function of a three-manifold built out of such tetrahedra. As I say, figure-8 knot is an example which is easy to do in this perspective. You compute partition function like this, show that it's a topological invariant. It follows from so-called Pachner moves that tell you that no matter how you glue this tetrahedra, the result is going to be the same, and you obtain a nice expression. And this is, if you wish, another way to verify that the twisted superpotential that you obtain in this correspondence gives you exactly the same algebraic curve as we saw on the previous slides. So all of this begs the following question. If there is any nice dictionary that allows you to relate gluing of tetrahedra or perhaps other building blocks in three-manifold territory to some set of rules that allow you to construct general n equals 2 three-dimensional gauge theory out of basic building blocks, for example, theory T1 that I described earlier, and its close cousins. Very much like in AGT correspondence, we had to know only very few basic ingredients, namely pairs of pans and tubes that allow us to produce arbitrary Riemann surface by gluing. In the same way, we can try to chop any three-manifold and basic elementary pieces and hope that there is some standard model of n equals 2 three-dimensional gauge theories that's behind the scene. As I alluded to in this talk, and as Davide will explain in his talk, this is indeed correct. There is a very simple set of rules. To me, it's actually surprisingly simple, because naively I would expect something more complicated. And this is based on joint work in progress with Tudor and Davide, and he'll explain it in the following talk. Thank you very much.
Any questions for Sergei?
So in the usual case of R4, right, for omega deformation, you have this epsilon 1 and epsilon 2, which rotates one of the R2s and the other R2. And then in the case of S3, what does omega deformation mean?
Omega deformation is also associated to symmetries, or as Nati Seiberg explained in his talk, killing vectors. In this case, the symmetry group of a three-sphere, of say round three-sphere, is SO4, and it has maximal torus, which is U1 cross U1. These are again two symmetries that you're trying to rotate around.
So you're selecting some plane in the S3 and then sort of rotating it. Like, is there a geometrical sort of intuition to this rotation?
Yes, except that I wouldn't call it a plane, because three-sphere is very round, and it doesn't have a nice origin. It surrounds the origin in some sense, and rotation is a rotation around that. Yes.
Thanks. And at the beginning of the talk, you mentioned something about mapping to the Langlands dual group at the beginning. So could you elaborate on that?
Oh yes, perhaps I forgot to mention in passing that when we made identification of parameters, as soon as you see that h bar in Chern-Simons, SL2 Chern-Simons theory is related to b, proportional to b squared in Liouville theory, or epsilon 1 over epsilon 2 in aspect ratio of this squashed three-sphere, you immediately see that simple geometric symmetry that exchanges epsilon 1, epsilon 2, or symmetry b goes to b inverse in Liouville theory is simply the transformation h bar goes to 1 over h bar. So symmetry, which is totally mysterious from the point of view of Chern-Simons theory, becomes nice manifest symmetry in this framework. And surprisingly, all these partition functions, SL2 partition functions, inherit this property. And as I say, for a long time to me it was surprising and unexpected, because from Chern-Simons' point of view, it's hard to explain where the symmetry comes from. But here I think it's simply a consequence of symmetry between epsilon 1 and epsilon 2.
Any further questions? I think no. Let's thank Sergei again.